Hi everyone, this is Miriam Naime from the Alan Turing Institute and Newcastle University. Welcome to our Supergen Smart Charging webinar series. The webinar is an activity of the Vehicle Grid Integration Group at the Turing. The Turing is the National Institute in the UK for data science and artificial intelligence. And one of the objectives of the Institute is to apply data science methods to real-world problems, such as what we are doing at the Vehicle Integration Group, where we are contributing to the decarbonization of transport and electricity infrastructure. We've hosted several episodes already on the webinar on topics ranging from communication protocols for electric vehicles, cybersecurity, and charging infrastructure rollout plans regionally and nationally. If you search for Smart Charging webinar, you can find the landing page and the YouTube playlist. We're hosting a couple of upcoming ones on the next week. It's going to be on vehicle to grid specifically, and the week after it's going to be focusing on cybersecurity with industrial partners. Without further ado, I'm delighted today to host two speakers from Idaho National Lab who will talk to us about some of their electric vehicle projects. Barney and Timothy have extensive years of experience in the automotive industry, but also on electric vehicle projects. As you can see in their bios, they are leading projects for the US DOE on electric vehicle infrastructure, and the whole team at Idaho National Lab are really sharing a lot of insights and doing a lot of work on electric vehicles and charging infrastructure for at least the past 10 years. So again, we're delighted to have them with us and to share with us their work on their projects. Barney, over to you.
All right, thank you. I'm going to share my slide. There we go. All right, well, thank you. This is Barney Carlson. I'm going to be presenting on some of the current ongoing work for cybersecurity of high power EV charging infrastructure. This project looks at it from a consequence-driven basis for prioritization and as well as for analysis and evaluation. So I wanted to introduce the subject with the importance of cybersecurity with respect to EV charging infrastructure. Many of you probably already agree with this and know, but I really want to reinforce this point. The reason why is, first off, electric transportation is one of the first mobile loads that connects to critical national infrastructure, the electric grid. All other loads currently are stationary, but EV electric vehicles are one of the first to be a mobile source. And in the U.S., it can, a vehicle can go from the different regions of our national grid, from the WEC to the Texas Interconnect, and et cetera. So it can cross boundaries relatively easy in a relatively short time. Also, safety is a large concern because the public is able to use and interface with these high voltage and high current systems, especially 350 kilowatt charging that is emerging and now being installed, throughout many locations. And then thirdly is public trust. If there's issues with the trust of electric charging infrastructure, that will undermine all of the electric transportation because the charging infrastructure is vital to charge the vehicle and therefore have functionality of the vehicle. It's pretty obvious. Through our project, we like to reference this NIST security framework because we agree completely with their thoughts. I at least wanted to introduce it of the idea to identify and protect against potential threats and vulnerabilities of cybersecurity, then to detect and respond to a security event as it's happening, and try to maintain a minimum operation, and then recover from this event to regain normal operation as quickly as possible. There are two main takeaways I wanted to present for today. One, a large negative security event could have a significant or cascading negative impact on EV growth, EV electric transportation industry as a whole, both in regulatory, government policy requirements, as well as public opinion. And then secondly, cybersecurity is not a definitive mark. It's not, yes, the system is now secure, let it be. My point is, with enough time and skill and resources, a malicious attacker or a team of malicious attackers can compromise any connected system. Some systems are very secure and it might take a lot of time, but if they're very motivated and have a lot of resources, it is extremely likely that they will have some success of some vulnerabilities. So with this, it's important to know how to minimize this impact when it's compromised. So for the current ongoing project that I'm presenting on today, it is focused around high consequence events with respect to high power EV charging infrastructure. The team is made up of 3 national labs, 2 EV charger manufacturers, and 1 organization, charge point service operator. Sorry, I missed that word. So it's Idaho National Lab, NREL National Lab, Oak Ridge National Lab, ABB, Tritium, and Electrify America. With this project, we quantify and prioritize these conceptual high consequence events. We prioritize them and rank them based on a quantitative methodology I'll show on a next slide. We also evaluate this in a laboratory setting to determine how bad is the severity of the impact of an event, as well as we look at cybersecurity complexity, meaning how difficult is it for assailant to gain access to and manipulate a system. Later in the project, we'll be developing and evaluating mitigation solutions and strategies, and then finally, publish findings and solutions. So we categorize these high consequence events into 5 categories. First off is impacts to the electric grid. Second is hardware damage that could be to the vehicle or the charging infrastructure. Third is safety, could be public or occupational safety to the driver or to anybody passing by. Fourth is denial of service. And fifth is data theft or alteration. So with respect to the ranking and prioritization of these high consequence events, once first step in the project, we hypothesized with all the project partners a list of well over 50 high consequence events that we felt were plausible and would have impact. But with this, which of these 50 should we really dive in depth and concentrate and focus on, given limited time, limited resources, whatnot? So we prioritize these using methodology. Could be familiar to you as a failure mode analysis in similar manner. And we're looking at it from an impact severity score, how bad would this event be? And then also the cyber complexity multiplier score, meaning what is the ease of cyber manipulation? And the highest ranking score would be one that has a high impact severity and a very easy means for cyber manipulation. And with that, those would be the events that are focused on most throughout the rest of the project. So with that, the the list of well over 50 high consequence events were boiled down to 23, if I recall right. Even that's quite long. So I boiled it, I'm showing the top 6 here, several of them with respect to grid impact, several with respect to safety. The top one was the sudden load shed from multiple XFCs. That's an extreme fast charger, which is 350 kilowatts of operation. If there was a way a malicious attacker could cause multiple fast chargers to simultaneously shut down, our testing in the lab has shown that at least one manufacturer unit shows 2 milliseconds to go from full power operation to standby, which is quite quick. And especially if a malicious attacker can coordinate that to have an entire XFC site of half a dozen or more chargers shut down concurrently, this could be a few megawatts of load shed within milliseconds. Secondly, there's a few safety high consequence events, such as a shock or burn hazard from a damaged cord set. If a malicious attacker can disrupt the thermal cooling system of the liquid cooled CCS high power charging cable set, this could cause damage to that cord set, which could cause a burn hazard, or even if the insulation fails bad enough, it could be a shock hazard potentially. And then another safety high consequence event is based around wireless charging, which is also in the scope of this project. As many of you know, wireless charging is based around a magnetic resonance. With this, there are stray electromagnetic fields that surround a wireless charger, and it is kept within safety limits due to good engineering. But if a malicious attacker can request the ground side of this wireless charger to energize without a vehicle present, this could cause a potential safety hazard for somebody walking over the ground side system, especially if they have an implanted medical device. I'm not going to go through the rest of this list. I just wanted to introduce as a high level some of the highest prioritized high consequence events. So in our lab, we do have a 350 kilowatt fast charger, and we did a cybersecurity assessment of this unit. It involved a 4-step process. First, it was identify the attack pathways, such as local connection, physical access, cellular access, etc. Secondly, identify the vulnerabilities, especially through known vulnerabilities, such as open SSH, which through our research, there are no known vulnerabilities, known critical vulnerabilities. Excuse me. We're looking into OCPP man-in-the-middle style attacks that's currently underway. And from our findings initially, we're seeing that physical access has the greatest risk, not only because an assailant could actually plug in and connect directly to CAN bus or other communication areas inside the charger, but it's also greatest physical risk to the assailant because of the presence of high voltage. So that's an aside. Next, as part of the assessment, we attempted to compromise the system, and then in later stages of this, we're going to be providing mitigation recommendations. So let me briefly highlight, with respect to time, I have 10 minutes left. I want to highlight the sudden load shed that I spoke of before and introduced before. This is a snapshot of the high power fast charger only operating at 128 kilowatts. But as you can see, it shuts down on the graph on the right in 2 milliseconds from full power operation to standby operation. So this is quite large. And there's multiple means we found of getting a shutdown to occur, either through OCPP or through a charging error state, that if there's a CAN bus error state, it will shut down, or even just a normal stop charge request, either from the vehicle or from the user standing at the front panel of the charger. So with respect to this sudden load shed could have a potential cause for distribution feeder instability, and that's what we're studying right now with hardware in the loop modeling at Idaho National Lab. We'll have some answers on that as to how significant is this. So more to come on that. Oh, which is exactly what this slide is showing here. So this is what we're working on. This is we're using an RSCAD model on a 39 bus system to evaluate and look at parameters of how many XFCs in clustering, proximity, and even power level are needed to cause a significant disruption, so that we can validate if our previous assumption of prioritization was correct, or is this really not as big of a deal as we're assuming it could be. Moving on, the cyber complexity of the liquid-cooled cable set, where I spoke before that it could have a, if the liquid cooling is manipulated, it could cause a potential burn or shock hazard. Through further investigation from the cyber complexity standpoint, the ranking of this HCE is much lower now because of two industry standards that already exist, which recommend or require the vehicle inlet coupler to actually have temperature measurement as well. So even if the charger side is manipulated by a malicious attacker, if the vehicle is correctly measuring the temperature, it will request the charger to derate and reduce current. So therefore, this is a much more difficult cyber vulnerability to manipulate, because both the vehicle and the charge system would have to be manipulated concurrently. Very difficult. So the conclusion from this slide is we've therefore reduced the scoring and prioritization of this high consequence event. I wanted to say a few words about the wireless charging operation with no vehicle present. So here's a picture of a bus stop where a wireless charger has been installed for a transit bus. This one's 50 kilowatts. But as you can see, customers will be walking back and forth and waiting at the bus stop. If a cyber malicious attacker can actually energize this ground side of the wireless charger, and a person walks over this wireless charger, they could actually start to couple with, especially any metal objects on them in their shoes or keys in their pocket or implanted medical device, could be a potential public safety issue. And also, we're looking at other high consequence events with respect to grid impacts. This one is non-responsive, for a charging infrastructure to be non-responsive to load management, such as manipulation of OCPP or other smart charge management communications. So with this, we're actively researching OCPP right now because it is utilized by many charge infrastructure installations, and I think it's quite a good solution, to be honest. But if there are vulnerabilities that can be manipulated, this could be of concern. So hence we're focusing a lot of efforts in this area, and we have a local OCPP server set up connected to several of our DC fast charge stations, 350 kilowatt, 50 kilowatt, etc. So looking towards the future, we're going to complete the assessment of these highest prioritized high consequence events in our lab and with our project partners. secondly, we're obviously going to create and publish recommended solutions to try to harden attack surfaces and close vulnerability loopholes, as well as methodologies to safeguard information, identify occurrences, and respond to these malicious events. So in summary, I've shown that we have a list of high consequence events for high power charging infrastructure, and we have prioritized these based on impact severity and cyber complexity. Red team assessment findings are showing good results on the high power charging infrastructure in our lab. It is very secure and it is very difficult to compromise. As I said before, the most likely means is actual physical access, which is not a good idea due to the high voltage concerns inside for the cyber malicious actor. Additionally, prioritizing these high consequence events has really given our project guidance and has prioritized the lab evaluations for our projects so that we concentrate on the most important aspects. And then moving forward in the project, we're going to be developing mitigation strategies and solutions, as well as publishing results and findings. That is it for my presentation. Is it time for questions?
Yes, great. Thank you so much, Barney. So what we'll do now is we take 10 minutes Q&A for the cybersecurity questions, and after that we move on to Tim's presentation on the Caldera platform. To start with, a couple of weeks ago, the European Network for Cybersecurity and ELAD organized a workshop on cybersecurity of smart charging. And one of the things they shared is that a repeated switching of around 1 gigawatt can cause a national power outage in the Netherlands. And they also think that an estimate of 3 gigawatt of repeated switching can cause an outage in the EU. I saw some of your slides about load shedding. Do you have an estimate of how much could cause an issue?
I don't have an answer for that yet. That's exactly why we're trying to study this with power hardware in the loop here, because it's also dependent upon the distribution feeder loading, as well as, at least in the U.S., some sections are rather old, meaning in the Northeast, New England area, the electric grid is a little older. Whereas in some other parts of the country, there are newer interconnects and components. So that's exactly what we're trying to come to an answer with to at least advise the U.S. Department of Energy as to how big of an impact could this possibly be. But thanks for the question.
Thank you. Are you in touch with the European Network for Cybersecurity and the ELAD guys working on cybersecurity?
I'm sorry, are you asking, have we been in touch with them?
Yes, or are you in touch? Because there seems a lot of synergies in your work, and especially what you're doing in hardware and the loop. I don't know if they're doing that, but that's definitely something interesting, and maybe you should be in touch if you're not.
Yeah, we should be. Can I ask you about that offline?
Yes, of course. I'll put you in touch.
Thanks.
We have questions on, you mentioned OCPP. So you assessed OCPP 1.6. I'm wondering if you have tested OCPP with the security white paper that came after it to deal with some of the issues with the security in OCPP 1.6. And also, what about OCPP 2.0.1?
Yeah, we focus on OCPP 1.6 because that's what a vast majority, at least in the U.S., of what we've seen implemented. We do understand that OCPP 2.0 and more recent versions do have encryption capabilities, and hopefully that's the solution that we'll see of improvement. That, hey, if there are vulnerabilities that we find, hey, look, hopefully the newer versions already come with a solution. That's what we're in the middle of now. So yes, I agree. Thank you.
Yeah, so for the OCPP 1.6 for companies in the US still using that and did not migrate to a newer version, there is a security white paper that they can have a look at, which improve the security of OCPP. And maybe you've already answered this, but are you doing any plans for OCPP 2.0.1 penetration testing?
So to your first comment, OCPP 1.6 and the security white paper that, yeah, that also comes down to implementation.
Yeah.
Because it's optional, to my understanding, that it's not mandatory for implementation. And from what we've seen from the half dozen or so vendors that we've looked at, their systems, they've either chosen not to implement it because of time and cost, and it's not a necessity, or the implementation is very minimal, and there's perhaps a mistake or two. I'm not going to talk to any specific manufacturer, of course.
And exactly, your
and
work.
Yeah.
I was going to say exactly your work and what you're doing showcase the importance of implementing the security aspects, even though it's not mandatory.
Yes, I agree. And for your second question, OCPP 2.0, we don't have plans currently to investigate that, at least in this year, because we're still focusing on what is the predominantly used protocol in the U.S., at least for now. So I know I'm going around your question. I apologize, but that's the reality of our project for now.
Okay, no, that's fine. Thank you. Another one was for the horizon for IEEE 2030.5 testing under IEEE 1547 2018. I don't know the IEEE one, like the 1547, but I'm aware of, we had a webinar on IEEE 2030.5 and there was a lot of security included in that protocol. So I don't know if you have looked at it.
We've been focusing on, yeah, understood. We have not been focusing on that for this project. There are so many different vulnerabilities that could be looked at, and that's why we did the prioritization at the very first step of the project, because if we had 100 different things to look at, we would have needed a much larger project. So sorry to say that we're not, that is not one of the focus areas of our project currently, but it is important. I'll agree. Thanks.
For the real-time digital simulation, was a physical battery used in this testing, and what size of battery to apply? 350 kilowatt and 128 kilowatt of high power. I'm just reading a question now.
Yeah, that was actually a bus. Technically, it's this bus in the picture, as you can see here. I'm not going to tell you which brand, but I'm sure you can figure it out. And this was the response of, it was charging at steady state, and we stopped the charge event in several different means. They all were nearly identical in stop charge response. They range from 3 milliseconds to just under 2 milliseconds. So that's why I'm saying, well, the ramp down rate is about 2 milliseconds. And most of the time, it was just the variability of when in the 60 hertz cycle did the stop charge request initiate. But, well, that was maybe too much of an answer, but thanks, that's it.
Another one is electric vehicles can move across different grid interconnections. Are there any specific threats that arise due to this mobility of EVs across different grid interconnections?
Oh, yeah, especially if the vehicle can be a transport mechanism for other type of malware to be uploaded to charge stations. Therefore, this malware can have an impact on a distribution network in the WEC, and then cross state line and have the same impact on a different different areas. So it's that hypothetical transport mechanism.
Great.
Not easy, but possible.
Yes, so some of the findings are most likely sensitive. Are you planning to share what you're working on publicly in forms of reports?
That's a great question, because we have to be careful with this. Our method of disseminating information is, first we go to the manufacturer in which we're working with their hardware, and we disclose this information per the non-disclosure agreements that we already have with several manufacturers. We would come to an agreement as to what portion and to what extent of that information can we publish, meaning if it's business sensitive to that manufacturer, we might not be able to publish, or highly likely not publish, all the information, but we should be able to publish an overview of the essence of the vulnerabilities, and then our research is where we come up with mitigation solutions or creative means of preventing and responding to a certain type of event. So.
Following those findings, do you considering how closely you work with the US DOE, and you are a governmental body, do you foresee a change in the grid codes where cybersecurity in certain communication protocols, or in general for electric vehicles, becomes mandatory?
That's a good question. That one is tough, especially since it boils down to who is allowed to, dictate rules and requirements and standards and regulations. As a national lab, we can provide technical results and perhaps advice to other agencies, but in no means can a national lab try to change regulation and whatnot. So we're trying to stay focused on the technical impact, severity, and cybersecurity complexity, and provide advice and recommendations. But then any changes or requirements or standardization is not within our scope or focus.
Got it. Okay. So for the things you are able to share, such as the presentation, some sort of reports, maybe some data, where can people find this information?
Good question. We do have a website at Idaho National Lab where we can share that. And I didn't put it on these slides. I can share that with you afterwards, and you can disseminate it to the group.
Yeah, absolutely.
Yeah, that might be best. Perhaps it's on Tim's slides as well. I'm not sure.
Great.
I believe it is on my last slide.
It is excellent.
Yeah.
Okay, great. Okay, so on that note, thank you so much, Barney. And then it's over to Tim now.
Great, thank you.
Great. Let me just set up my screen. The slideshow. Great. Is that working for everyone?
Yes.
Great. So good morning here in the US. Good afternoon there in Europe. My name is Timothy Pennington. I'm a senior research engineer here at Idaho National Lab, along with Barney, who happens to be the top center in my photo, working hard in his lab. I wanted to speak today not about one project specifically, but about a tool we're developing, a software tool called Caldera, which is a modeling and simulation platform for representing and researching electric vehicle, grid, and stationary energy interactions, and possibly more. I'll get to that at the end for our future work. Just quickly, because I know we have a very broad audience, I wanted to sort of introduce Idaho National Lab. We are one of, I believe there are 17 national labs in the United States under the Department of Energy. Idaho National Lab is known as the National Nuclear Energy Laboratory. So we were founded out here in the desert of eastern Idaho. There you get a little map and then a quick zoom in of our very large space. We're 890 square miles of predominantly high altitude desert. And there are several reactor research facilities out there. Many historic reactors that no longer operate, but several test and research reactors currently, and efforts to build new next generation small modular and micro reactors. But our work is actually in the town of Idaho Falls. There are many labs doing a wide variety of research beyond nuclear, pretty much all related to energy in some way or another. So we're divided into 5 directorates at the lab, and I highlight the 2 here on the left that our groups work mostly with on electric vehicles. So there's the Energy and Environment Directorate, where our group works on advanced transportation. And there are also efforts in environmental sustainability, clean energy, advanced manufacturing, and biomass energy. And then we partner closely with National and Homeland Security. Barney's project, you can obviously see, reaches well into those spaces. And there we're able to tap a vast research or a vast resource of cybersecurity and critical infrastructure security researchers. Just a quick highlight of sort of zooming in. This is one of our larger facilities that our group works in. So this is the Energy Systems Laboratory. And within this, in this one high base space here, you can see there are several different laboratories. Our space, which Barney manages, is largely here on the left, the Electric Vehicle Infrastructure Laboratory, EVAL. And so you can see our 3 vehicles and several of our chargers placed here. In the middle, there's a high temp electrolysis hydrogen generation group. And then on the right, we have grid emulation and microgrid research sections. And outside this building directly, they have some solar, some wind, some large scale flow batteries, and other distributed energy resources. And there's currently, actually this photo is out of date because there's a whole lot more development that has happened in here, specifically looking to interconnect these different laboratories under the integrated energy systems concept, right? Where we're going to be using various distributed energy systems to power all of our electrical needs, including electric vehicles. And so in this space, we're able to do that and physically connect. And this is where most of the hardware in the loop testing that Barney mentioned is able to happen. And now that's happening all the way upstream towards grid emulation and microgrids. Specifically our group, and I'll be quick here, but we are sort of, our history is largely focused in battery development. And so I think of our research organization as a continuum. We start on the far left here in molecular level material studies for batteries, designing new electrodes and cathodes and a lot of chemical engineering. And then we move toward battery characterization and testing. So we have a large facility shown here in the bottom left called the Battery Test Center, which has, I think over 100 channels for testing batteries in environmental chambers, where we study the performance of individual cells. We do that, to support our research in advanced materials and batteries, but we're also a third-party tester for many of the large auto manufacturers and other battery labs. We have decades worth of data collected on these batteries, and I'll get into why that's important for our current efforts in research. In the middle bottom here, we have another lab that's non-destructive battery evaluation. So that's pushing batteries really to their limits of this, for example, is a vibration table here. but not intentionally destroying them, just pushing them to their limits to validate and test their performance. Most of my talk today will focus on the far right of our research group's spectrum, and so that's sort of future electrified mobility. So that's thinking more about how we electrify all forms of transportation beyond the light duty vehicle and what the impacts are of those vehicles back onto the grid and how to control and mitigate any negative impacts. We're also looking at, really forward thinking electrified mobility such as robotaxi, self-driving vehicles that would be electrified, and drone package delivery and what the electrical needs will be for that and how to optimize it. So my talk today is about this tool, the software tool Caldera that we've created. And so I figured I should start with at least a little bit of background of what is this, where did it come from? Perhaps I should have had a slide that said why Caldera. Why did we bother to go create this new tool? We have specifically designed Caldera to work with other existing models, but for the explicit purpose of improving the study of electric vehicles and their impact on the grid. So we think of Caldera as living in the middle between these other pre-existing models. On the left side, we have transportation models. These are a couple of examples, Polaris and Beam, but I'm sure you could think of many others. These come out of other US national laboratories. But there are many good transportation models which accurately represent how vehicles will move around and how people will travel through space. Which vehicles will they use? How much energy does that consume in aggregate? And then on the right-hand side, well, I guess I should say, but the existing tools here have failed to understand anything about the grid, the distribution networks for power, power availability, the costs of electricity, and detailed the battery charging profiles of any of those vehicles. So they may have thought about the total energy needed, but not necessarily how and where that energy is coming from and what it looks like in detail. On the right-hand side, you have grid models. These are some we work with regularly, OpenDSS or GridLab-D, which do a great job at modeling your distribution network and what its capacity is and how much power is moving down the lines, but really has no understanding of transportation. As Barney pointed out, electric vehicles are now this very mobile load, and so the distribution network has never needed to consider loads that not only change in time. Of course, there's lots of research in air conditioning loads and business loads, heavy manufacturing loads, and how those might have a temporal distribution. But what about adding a geospatial distribution of where and when these high-powered loads are connecting to the grid? So we developed Caldera working in the middle. It uses Helix, a co-simulation tool, but Caldera is not just co-simulating these two other tools against each other. Caldera is built on a whole library of high fidelity battery charging models, and I'll get into that in just a minute. And it really sort of translates the energy demands of the transportation over to the supply of the distribution. And we think there are many applications for that in studying all forms of electric vehicle impacts. I'll move quickly through here. This is just sort of a deeper dive view at how Caldera is built. So like I said, living between transportation and distribution networks. But I will say Caldera is an agent-based modeling platform for predicting detailed system impacts and demonstrating intelligent management strategies. So through the high fidelity charge models, and by being an agent-based model where every vehicle is accurately represented and tracked throughout the simulation, we can accurately represent what the loads and the impacts are on the grid. And now we've also built in the capability to implement management strategies on top and assess what their resulting impact is, and thus what the value of those management strategies are. So I suspect the audience here is quite well informed about electric vehicles, so I'll move quickly through this. I'm sure you're all aware, right, that each electric vehicle has its own characteristics, so its own size and charge rate and charge profile of the exact battery pack that has been designed and installed into that vehicle. And you're probably also aware that it's going to perform differently on every charger that it's connected to, based on what the chargers, charge rates are, power factors, efficiency levels, etc. So through a lot of our testing, both battery cell level testing of understanding the chemistry and the charges, and also our testing in the electric vehicle infrastructure laboratory on many different brands and types and models of EVSE supply equipment, we have generated this library of detailed charge profiles. So you can see that, a light duty vehicle being connected to the various chargers at various charge rates will result in different profiles. Here's a little bit more on that. I guess maybe I should have flipped slides a little faster, but I just wanted to say, these models inside of Caldera that are the foundation, they're individually based vehicles. So that's that agent-based piece, not aggregate or composite models that have been used in other forms. We don't say what we think the population will include 200 vehicles in this geographic area, so we need to supply power and we need to install chargers of this much aggregate load. We represent each vehicle. And then this series of graphs here is just to say, the red is the models that we've created, and then we've gone back and validated these models against additional laboratory testing. So the gray shows you real world lab testing that we've done either on vehicles, whole packs or cells to represent, these different qualities within the charge profiles. Okay, so from that, vast collection of data that we've amassed in our research over several decades, we've built this tool now as a grid impact demonstration platform. So the transportation simulations, or some version of transportation data, and I can get into that, the various things that we've studied and how we apply vehicles, but as an input to Caldera, basically, we apply these vehicles as loads connected to the grid. In this example, so inherent in Caldera as a tool, we've built this, what I like to think of as a digital test bed or a sandbox for exploring notional control strategies. And so we use the IEEE 34 node feeder, which is known as a long, lightly loaded residential feeder. But we could implement many other feeder styles, and in several projects, we're implementing real-world feeders given to us through the proprietary data of the utility partners on our research projects. But so inherent, we have this IEEE feeder. We apply some EVs. So in this example, we've applied 50 EVs at each one of these edge nodes to represent a 200 vehicle load across this feeder. And then we go ahead and we give them each real world charge data. So we've estimated how many vehicle miles they've traveled each, what their battery size is, how much energy they're going to draw to achieve their full charge for the next day's driving. And you can see the results over here on the right. The black is the pre-existing power of the feeder, and the red is an uncontrolled load caused by these additional 200 vehicles. So you can see substantial increase. I think it's like a 30% or a 1/3 increase on the power, the peak power of the feeder. Also shown in the bottom right, because we're using OpenDSS as our grid tool integrated with the Caldera platform, we're able to also model what the resulting voltages are. And for those that aren't power systems engineers, like I was not before starting in on this project, generally the range from like 5% above the notional voltage to 5% below that 0.95 are acceptable voltages to most utilities. But you can see here several of our nodes are falling well below that by this load. And so we can expect and see that there are negative impacts happening on this notional feeder with these vehicles. And you can also see through these step changes in the grid or in the graph that some of the built-in voltage regulation tools on the utility are functioning, but they're failing to keep up with what's happening to demand. So in our notional platform, why I think of this as a sort of digital sandbox, we've implemented several control strategies. Actually, my colleague Don Schofield spoke to this group, I think about a year ago, about some of this research that was happening. Under that project, they developed a centralized aggregator. So this assumes you have communication and control of every vehicle that's on your system, and you can apply a receding horizon algorithm to optimize when each of those vehicles should charge. So that's the green graph shown here. And you can see it does extremely well. It does not increase the peak power at all. It turns on the vehicles late into the night through here, filling in the trough of the curve, if you will, which might be beneficial for consuming, say, excess wind energy during the evening, which is otherwise curtailed. And it also, the aggregator is designed to ensure all vehicles are fully charged before their itinerary has them departing from home the following morning. So it achieves the transportation needs and it optimizes the electrical usage throughout the evening. However, it's highly costly in terms of communication and control. We don't have all the right protocols and hardware in place currently to do this. We're not sure who the aggregator would be, who's going to take this on. The utility doesn't want to be switching on and off vehicles, etc. So we're exploring several other control strategies. I don't need to get into each of these, but I'm sure you've seen time of use rates being applied by utilities. We show in purple here that time of use can actually be nearly as bad in terms of peak power on this particular residential feeder. So you haven't really improved your capacity, and you've introduced this massive step change, which could be a problem. And you can see down in the voltage curves is a major problem on resulting voltage at that very rapid increase of load. So then we've explored some random start, totally decentralized control strategies. And you can see there's good results from those, and they're relatively simple to implement. If you tell the vehicle when you need to start and you say, start charging at some random time, that will still achieve that. So now we've displayed the impacts and we've applied some control strategies to power shifting. We're also working on, and Caldera is capable of looking at these voltage issues. So as I mentioned, there's some voltage supply issues. So we're looking at control strategies that would support the voltage through reactive power. If you're familiar with the photovoltaic industry, they have done a substantial job of implementing 4-quadrant smart inverters with all of their installations. And they have the opposite problem, right? Where when they're creating generation, they cause voltage peaks, spikes, where we're causing voltage sags. But through those 4-quadrant inverters, they're able to supply or consume reactive power, equivalent to and in assistance to the grid, and thereby provide more real power through their solar supply. So we can do the same, we think, and we're working to assess the value and the impact of a solution like this. You can see here in the graph, well, in the top graph, I'll just say we don't change the power very much, right? So we're showing that this solution doesn't create a massive problem in the power provided over time, but it does have substantial improvements in the voltage over time. In the uncontrolled case, we're not able to get back totally within that 5% range, but in, for example, the random control strategy where we're doing the power shifting that's beneficial and applying this reactive power control, we're able to get back within voltage spec and have a better power profile throughout the evening. All of that work I've talked about up to this point has been on residential level 2 charging, which the Department of Energy here in the U.S. has certainly gone after first, as it's the current, predominant charge path, and I think it's considered that it will remain a large contributor to charging of electric vehicles due to costs. But we also recognize that increased adoption rates of electric vehicles are largely dependent on public charging infrastructure. If you're going to assist folks who live in multi-unit dwellings, apartment complexes and things, and don't have a garage that they park in and own and can install their own level 2, we need to have high power charging stations. So Caldera has also taken on the task of modeling, representing, and testing control strategies in this space. How am I on time? I will endeavor to move quickly here, but I think it's an important piece of work that we're doing and a new research space. So Caldera, we took Caldera and we said we want to have, sort of a fast charging station similar to today's fuel gas station model. So we want to have 6 chargers, and we want to have real world vehicle arrival and usage throughout the day. So we gathered, so we built a station in this model which has 6 350 kilowatt XFC chargers. And then we gathered real world data. Sorry, I'm skipping over here, but so we created these vehicles. Several of our other projects use these sort of prototypical vehicles that represent classes of vehicles. I'll get into that in just a minute, but we have vehicle characteristics, then we apply those vehicles. We got some real world data from EVgo, a charge network operator here, and used their data to bound it by busy gas station data that we also had, and created this sort of flow rate of vehicles through the charging station throughout the day. I'll show that. But it does represent a very busy station in a maybe very populous urban setting with 46% utilization. And then, okay, so here we go. Here are the types of vehicles. So we're representing 3 different classes of vehicles, and I'll show results from each, but we have a compact EV, so think maybe the Nissan Leaf in our market here has long been around at about, with a max charge rate of 50 kilowatts, so your DC fast charge, and has a relatively medium range of 150 miles. And then we have a current mid-size vehicle, so think maybe Tesla Model 3, which can charge at sort of Tesla supercharger rates of maybe up to 150 kilowatts. And then we're trying to look towards the future with higher power charge rates. So currently the market on the vehicle on the market that most accurately represents this is the Porsche Taycan, but understanding that's a rather niche market, we're also using this prototypical vehicle to represent the future SUVs and more rapid charging vehicles that we know are coming. So we take these vehicles with their associated charge profiles and we apply them to this station. And for the example here, I've applied all Nissan Leafs to come and go from this charging station throughout the day. You can see their total power usage, or their peak power, is 320 kilowatts. That's probably not a big deal to most utilities. And this, even if the ramping is relatively rapid in here, the total power is not so great. So it's not a big issue. We moved to the mid-size vehicle, and we now have peak power that occurs multiple times throughout the day of 900 kilowatts. So we're approaching a megawatt of power. We now are probably a notable load on the utilities grid that needs to be managed, and these ramp rates are quite high, which could cause significant voltage problems to the distribution network. So now there's something to really work on. And then we apply those future vehicles throughout the day, and we start to really approach 2 megawatts of power and have very massive jumps in power. So I noted here that Electrify America, probably our largest charge network operator in the US, has publicly stated that Up to 80% of the station's electricity bill can be derived from demand charges due to these peak power numbers. So I ran some calculations against our simulation here. And if you used like a $15 per kilowatt demand charge, you could have a $25,000 a month demand charge on your utility bill, while the energy charge for the total amount of energy you've consumed might only be $2,000 or less. So apologies, it's all in dollars, but you can see the relative amounts. The demand charge really is the predominant factor here, and it is what industry needs to work to mitigate. So how do we do that? And I think everyone who's thought about this knows that stationary energy storage is probably the likely low-hanging fruit. We are already seeing many charge operators who are installing some level of stationary energy storage. So we've built a tool in Caldera to incorporate that, to lower, to apply a stationary energy battery, and also some station, sort of charging station site controls to optimize their use. So for this example, going against, so a little bit of an eye chart here. Let me try to explain. The orange is that same uncontrolled profile of the vehicles through time, with the 1700 kilowatt peaks happening. And then we applied a 500 kilowatt hour battery to the station. And so the gray line represents the charge and discharge of that battery through time as it's trying to assist the station. The blue becomes the resulting station power. It's the power that it's imparting on the grid, the impact to the grid. And the purple is the state of charge of the battery throughout the day. And so you can see that the battery really comes on and assists, and it makes this really nice level demand on the grid. Your utility is probably extremely happy with you that you're consuming a lot of power, so they're, have a great customer, and you're doing it in a really consistent way until the battery runs out of charge, and now we get breakthrough, what I call breakthrough, and now we're still hitting substantial peak powers, which have impacts on the grid and also drive those demand charges. So the response, sorry, I had highlighted all this so that I didn't have to point at it with my mouse. You can see it's working well. It continues to work well, but here we get the breakthrough. So in hindsight, as we're doing this, we can simply change what I call the threshold, the control threshold. So previously, we were telling the stationary energy storage to let the station draw up to 600 kilowatts. Now, if I say let it draw 800 kilowatts, you can see that actually the effects on the grid will be more volatility throughout the early day, but we're able to control and manage through all the way through the day and avoid those peaks. And so again, just a little bit of math. Caldera is not an economics tool, but just my own back of the envelope math. That 500 kilowatt hour battery might cost about $500,000. We've done some research that shows $1,000 per kilowatt hour is a good number. So if we reduce that 1700 kilowatt peak down to like a 725 peak, so I haven't shown a true optimization here, right? But I could do better than 800, and I can see that because the SOC of the battery, the purple curve, never nears zero in this simulation. So if I did lower it that much, it would decrease those demand charges by $15,000 at that same rate that I was using before. And based on that, we'd have a payback period of 33 months on this equipment. The stationary energy storage, could easily have a lifespan of maybe 10 years. Also something that we're actively doing research on. In the other cases with the other power levels and the other vehicles, I've done those analyses here as well, and they all three seem to come out with roughly a 3-year payback period. The smaller the battery and the smaller the power, actually the longer the payback period because you're not taking off such large peaks. But I want to say this is not enough, and this is where the research gets interesting. And I realize I'm even shorter on time, but I'm going to go quickly because this is part I really like. So how do we predict and set what that threshold is? As I noted before, it was in hindsight. We can look back at the day and say, well, we could apply a threshold of 800 and make sure we made it through the day. What if we had guessed wrong, right? So I note here, machine learning AI is obviously a very powerful tool in prediction. We can very accurately predict based on probabilities and previous data sets what the demand is likely to be. But even a few cars showing up to these high power stations are able to completely deplete the stationary energy storage and have the station incur substantial costs. So here, similar data set. I believe here I've actually, I didn't note it. I think here I've applied a 1 megawatt battery. And so I've been able to lower the threshold down closer to 600 and have smaller breakthrough here. So if you, so sorry, my notes over here on the right. You can see we've got this 1 megawatt battery. That's actually $1 million battery to install, and the payback period on it is not good. That's a whole nother optimization process that needs to be done for each station based on what the expected use rate is. But just these 4 or 5 vehicles here break through and bring us up over 1 megawatt of power, creating a demand charge for the month of $6,000 simply because these 4 vehicles showed up on this one day. So smart charge management must do more. What can we do to prevent those? What would we do with that $6,000? What would the charge operator do with those $6,000? So the options, we could close the station down once our energy is depleted. We could charge those last 4 EVs several $1,000s for their charge. I don't think that would work. We could close a few of our charging points and the line would become larger at our charging station, or we could curtail everyone's power, and everyone who's come in thinking they can get in and out in a 10-minute charge now needs to stay for 20 minutes. So more acceptable solutions might be, and what we're working on here, and I'll show you, is requiring reservations, creating price disincentives, and managing the end state of charge for other vehicles that are on the chargers. Why did I lose control? Okay, so we have a project called Direct XFC using Caldera. We accurately represent through that agent-based model every vehicle and all of their itineraries, trips, and stopping points over at least a week-long period. It may grow to be 2 weeks. We're using real-world data of real vehicles traveling around Minneapolis, Minnesota. And so we study several things. So first, we're looking at the uncontrolled state. These are the vehicles. We're talking about several million vehicles traveling. We're looking at scenarios out to 2040 for what the possible adoption rates would be. And the vehicles, they do their daily trips. Maybe they go to work and then they go and pick up the kids at school and then they go back to home, and we track how much power they use and where and when they'll charge. And in this, scenario, without any control or any implementation of our charge management, you're going to occasionally have the vehicles having to wait in line when too many other vehicles have shown up at the charger. The prices are going to be higher because those stations need to be sure that they cover their demand charges and bear that cost against the vehicles. And you could have possible negative impacts on the grid. So then we do independent station management. That's what I was previously showing. So we put stationary energy storage at each, but the vehicles, the stations have to make predictions about when the vehicles are going to show up and how much power they need to have in the battery and how to control that battery. It'll do smoothing. It'll reduce the load profile. It'll mitigate some demand charges. And those batteries might be able to provide grid services when they're not in use, providing power back to the grid, perhaps at night and things, which could have revenue for the station owner. But we still have those issues of breakthrough and possible high demand charges, or we're going to be setting those thresholds excessively high to mitigate the risk of the breakthrough and thus not seeing the maximum value. So we're studying a system, and this is an example where we wouldn't have stationary energy storage, but we direct and we schedule the vehicles. I've hesitated to use this word directing because we live in a free market and nobody's going to tell a vehicle where and when it has to charge, but what are our strategies to try to get the vehicles to charge? And so Caldera is now built with a tool where the vehicles, when they know their itinerary, so you pre-program your schedule and the vehicle knows where it's going and when it's going to be depleted on power and need to charge. And then it's going to query all of the possible chargers. So saying, along my morning commute, I have these two options. They add this much drive time, which adds this much more energy and cost, but they have an associated charge rate. They can refill me at a certain speed, and they have availability. I can place a reservation. Now I know I won't have a wait time when I get there, and they're prepared to provide me a charge at a specific cost. As a station builds up their reservation book, they might know that they're drawing too much power, their demand charges are going to go up, so they increase their price that they're offering to vehicles who are querying, and now they can incentivize vehicles to move to other charge stations. Perhaps this is even more beneficial if one company is the owner and operator of many charge stations. They can change the incentives to shift the vehicles to where it's most beneficial. Even better is, as shown in the previous site controller with a battery, if we do stationary energy storage at each battery and we have those communications for price and availability and we make reservations, we can charge the battery knowing that we have a vehicle coming and really optimize on the threshold that the vehicle is going to use. So this will reduce costs for the vehicles, reduce costs for the charge operators, reduce costs for the utilities by having smoother loads throughout, and also shifting the load profile where and when you need it. If you have a distributed energy system providing generation, maybe you have a large solar PV field in one area, you might want to incentivize vehicles to charge locally to reduce the congestion on the distribution network. So we're working through this now. We're in the second year of this project, and we'll have results this year on what the value of these types of systems are. I just want to say we're engineers. We try to think about a lot of the possible problems. So we're thinking about consumer relations and what are the responses going to be of drivers if we're telling them they can't charge here or there, that there are peak capacity places that need to have reservations. Maybe there are certain chargers or certain station operators who will say, I'm only a walk-in, first come, first serve service, and other operators will think, well, it's better to provide reservations, and thus we provide more diversity to the users. So we're building a system that would be based on, a communication and reservation platform with the vehicles. We're sort of investigating the value here. We understand to commercialize this will be a private endeavor with a private company, but we want to show whether there's value. This is something the OEM should integrate maybe into their cars to have communications of this type and display on the dashboard, or perhaps it's a third-party, app on your phone that allows you to place these sort of open tables type reservations through an application. And we also noted that a well-developed system could take into account what the charge rate impacts are on the longevity of your vehicle's battery. There's been lots of research that fast charging may have negative impacts, or charging to high states of charge rapidly may have a problem, may cause degradation. So we could incorporate all of that and help you understand where your most efficient use of your vehicle and your dollars are. Recommend, charging late at night at some far-flung location if you want to really pinch your pennies and save costs, or what's most efficient on your travel. So I just wanted to say we're working with several large utilities representing these areas. We have their distribution network data and are mapping it. And we also have transportation data that we've gathered from data providing companies for these areas. A little bit of OpenDSS grid studies, so just to show that we have this data and we're assessing where capacity exists on the feeders if you wanted to place XFC's stations in the right locations. And in all fairness, this is Sandia's work product, so Sandia National Laboratory is our partner on this recharge project, and they've done this. And other applications for Caldera, we're actively looking at at other applications, we see Caldera's battery model and control model as being capable of doing grid scale battery modeling. So if you think about, like, this is that Australian wind farm battery project in the bottom right photo, we could help with that. We've also lately been thinking a lot about distribution centers. So in the US, we have these large distribution centers with hundreds of trucks coming and going for Amazon package deliveries or any of our other big boxes, or maybe our carriers like DHL and UPS and FedEx. And currently those are often very minor loads on the utility, like 500 kilowatts to run their lights, their conveyor belts, their heating loads, whatever. But quickly, with hundreds of trucks becoming charging over XFC loads, we could be looking at many megawatts of power in these places. And so what does that look like to the utility? How do we minimize the peaks on that? How do we ensure that the infrastructure is available for that? Last mile delivery, you know, your smaller panel vans are going to have similar impacts. We're seeing electrification of municipal vehicles like rubbish disposal trucks and utility work trucks. We've seen several already electrified, at least in their ancillary power systems. So for the bucket that lifts the worker up to work on the utility pole, that's all becoming electrified. And so we're working on those. A large one I'm thinking about is long haul trucks. So similar to our regional transportation, a vehicle, you know, a truck traveling from LA to New York to deliver goods has options in drive paths that might take the same amount of time or cover a similar number of miles. But what's the charging infrastructure along those paths? Where can they get megawatt scale charging so that they can get back on the road quickly and cover more miles? Where do they have to do lower power charging and charge overnight while they're on their mandatory sleep break? You know, can they place reservations at each of these sites? Caldera, you know, we think could work well to model that. And while I had the floor with a diverse group of researchers, students, and professionals in the industry, I wanted to just say, you know, Caldera is a software tool. We are working to have a licensing process for it if you think you could make use of it. We have a current licensing process. Caldera is being used at other national labs and by a few industry partners that we have. We're working to increase our ability to do that, but also it's a research tool. It does not have a slick user interface where you can go and rapidly do what you want to do. So we would offer to collaborate. We think that's probably the best way to use this. We'll give licenses, people can use it, but we should be a partner on the project to help you set it up in the best way and make sure it's delivering the research results that would work for your projects. So feel free to reach out. Here's my contact information and also the website for our group, Advanced Transportation, at inl.gov or .inl.gov. And I think there are a bunch of questions that I've been ignoring. Thank you, everyone, for your time.
Great, thank you. Thank you, Tim. We've received several questions on specifically the access to Caldera, such as, is there a place where we can see Caldera in action through a demo or a video? Another question was about potentially available for use by other researchers. So I do encourage the participants to contact you directly to arrange such collaboration.
Yeah, we're working to a point where INL as a whole, the Idaho National Lab, is working to have a software store where people can just log in and request a license and download something. We're not there yet. I could pass that along when we get it close. But right now, the best is to reach out to any of us individual researchers, and we can set it up over email to get the license. There is an existing license and end user agreement. And we can share, we're not sharing source code, we're sharing executable, and we're sharing about half of it that doesn't include our artificial intelligence components. but does create a usable modeling platform. So
for
please
example,
reach out.
So you mentioned so it is not an open source platform.
Correct. At this point, it is not open source code. The Department of Energy, has paid INL to develop this code as a tool. So we've made it an executable, usable tool to others, but we don't have the source available.
Okay, so assuming we want to use the executable and we want to build a distribution network somewhere in the UK, and we have the information we need from the distribution network operator here to do so. Can we do that through Caldera? Is OpenDSS already there and allows input of, let's say, size of the transformer, number of the feeders, customer on each feeder, so that we can build that distribution network?
I believe what you're describing, all of the capacity would be there. Setting it up probably requires our assistance to show you how currently. We're always looking for more funding that will let us, sort of bring it to that final tool state where others can use it at will. Once you understood it, I'm sure you could. And if anyone wants to reach out on that, I defer the questions to our lead software engineer. I'm not sure if Don's on the line. Don, if you're on the line, feel free to unmute. Miriam, you obviously know Don, so feel free to reach out. He would be the best resource.
So is it Don who would be giving us a demo, for example, on the Caldera?
Yeah, so Caldera is, like I said, not a slick visual tool. It is an analytics tool, a research tool. So there's not a great visual demo to give. There's input CSV files and output CSV files, which we then turn into our graphic results. So I've shown you the best things to look at on Caldera, but if you wanted to actually work through a real problem where you had all the input data, Don would be the right person to do.
Okay. No, I'm specifically interested on the distribution network modeling aspect. What language did you write Caldera on? How did you manage to integrate OpenDSS in it?
Yeah, so Caldera is largely a C++ tool, but portions of it use Python as well, largely for initial development to move quickly. What you're seeing here, for example, I believe is coming strictly through OpenDSS. So you're not working in the Caldera platform on OpenDSS on these detailed models. But it's the co-simulation that happens. And so we co-simulate in, not necessarily real time, right? It's in simulation time, but in step. So as Caldera assesses what a vehicle is doing every minute or 5 minutes or 10 minutes, whatever the time step is that we're using, it's exchanging that information to OpenDSS, and OpenDSS is running it. As I said, this is run at Sandia, so we actually, can work back and forth in simulation time.
Excellent, thank you. Speaking about co-simulation, there are simulation tools specifically for cybersecurity. Have you thought about linking Caldera to some sort of a cybersecurity or security simulation tool and check a specific attack could cause this kind of impact on the grid?
We have not done that to date. There has been some thinking about it. Caldera is going to, we just were awarded a new project. It's an industry-led project that Barney is doing on cybersecurity of smart charge management protocols. And Caldera is going to provide the real-time data, or the real-world data of charge events that will be then hardware in the loop simulated, and the cyber attacks can happen. That's not your question about cyber modeling tools. So I guess no, we haven't.
Yes, no, but that's great.
Yeah.
Great, thank you. Have you modeled the electric vehicles as load What about if some chargers allow bidirectionality and those cars become also a generator?
We have not yet done any V2G studies in the U.S. I think it's largely seen as a standards issue to implement, and so Department of Energy has active programs on it, but has not funded other projects to think about V2G as well. Obviously, we as researchers are thinking about it. There's nothing in Caldera that would prevent us from turning a vehicle into a load. In fact, I went to this slide on reactive power because we have built the assumptions into Caldera on this example simulation where vehicles that are at 100% state of charge but are still plugged into the grid are able to provide reactive power back by having a few capacitors in their smart inverter, which can do the switching to create reactive power. And that's the extent of what I know about power systems engineering. So no more questions on that. But for example, Caldera is already providing reactive power back to the grid and simulating that. There's no reason we couldn't do V2G.
Excellent. Maybe this is related. Two questions. Are these EVs modeled as a PQ load? How is the power factor of a single charging unit determined? Yeah.
So sure. All of the details of power factor and efficiency and things are covered through these charge models. So every model doesn't represent just the vehicle, but represents the vehicle and the supply equipment as a pair. And we have data on what the AC load looks like. Does that make sense? So we don't accurately, we don't individually represent power factor and efficiency in each event. We represent the pairing of the EV and the EVSE.
Okay. And the other one is, does the voltage profile slide, so I don't remember which slide, represent data showing load tap change operations at the substation or another voltage control strategy?
This is load tap changes, I believe. Again, not a power systems engineer myself, but yeah, I think what you're seeing, right, are these load tap changers stepping through.
If we stay on that slide, you have the IEEE 34 node feeder. Are you able to model an MV-LV network? I mean, as long as you have the information, then you can put in a network that's not just low voltage. You can expand it to include several LV networks and the MV network above.
Yeah, we have not done that to date, but I don't know that there's any reason you couldn't represent it and study it upstream. Caldera is, really about accurately representing the loads and enabling that higher level modeling.
Got it. Okay. And do you have plans for a DER grid modeling? If so, is there a timeline?
DER grid modeling.
I'm assuming are you just modeling electric vehicles in Caldera and charging infrastructure?
That's correct. I mean, I would say that as we moved into the XFC stuff, right, and started to represent the stationary energy system, that's a distributed energy resource. Yeah. We're not currently doing work that dislocates the charger from the stationary energy storage, nor are we representing solar or wind as sources on our distribution network. But there's no reason that we couldn't, I believe.
The same as you mentioned, you are modeling EV as a load, but you could extend it to model it as a generator. The same.
And in fact, I think, as I mentioned, that we see uses for Caldera, regardless of electric vehicles. I'm thinking just about grid scale energy storage, grid scale batteries, we could represent those with Caldera. There's an internal project proposal, right? So this is not real work yet, but we're proposing work on using Caldera to also represent hydroelectric and sort of what's the stored capacity and how could we optimize spill rates and power generation rates at hydro using Caldera as a tool to do that.
I have another couple of questions about power factor and power quality. Would you like to take them, or should people send an email about them?
That's probably best. I just fear that I won't be very accurate in them. So Dawn Schofield would be the best resource, or email me and I will connect with Dawn. My email is at the end. I was just going to go back to this slide, which shows a little bit of our work on power factor and representing it for a specific charge profile here. So let me show my email. Please feel free to send me an email and I will get an answer to it.
Excellent. Thank you so much. Okay. Barney and Tim, thank you so much for your time. Would you like to add anything where people can find the information? You just showed the website, if people can contact you directly.
Yeah, thanks. This is Barney. I have nothing more to add except for, yeah, you're welcome to contact me directly, or the website as shown, or worst case, contact Tim. His email's up there and he'll, he's in the office 2 down from mine. So, well, not right now, but typically 2. Yeah, anyway, thanks.
Great. Okay.
Yeah,
well,
thank you.
Sorry, go on.
I was just, thank you, Miriam, for having us, and to everyone who logged in to hear about our research.
Well, again, thank you for sharing about the exciting projects you always work on, and I hope you do get more funding to expand this work and to get Caldera where you want to see it.
Thank you.
All right. Thank you, everyone. Bye.
Thanks. Bye-bye.